Hi, everyone. Today we're starting into section 2.4 and 2.5. 2.4 is all about determining the limits of functions. So more stuff on limits, but actually trying to evaluate a wider variety of limits than we have previously. And 2.5 will start into continuity for real, even though we've been mentioning continuity, fairly frequently so far. Hopefully the work that we've done earlier will pay off now, and this stuff won't be as crazy as it could be if you were just seeing it for the very first time. Okay, section 2.4, determining limits of functions. Here I have assembled 4 different functions that we might want to find the limit of, and they are ranked in order of increasing difficulty. The first one, we're looking at 2x plus 1. That's just a line. You can plug values into lines and get y values, and things work out pretty well. So a lot of times in limits, you're able to just plug in the limiting value. If this thing, if x is approaching 3, let's just try plugging in 3, and we get 7. And that's totally fine. Lines are nice continuous functions, and limits pretty easy in that case. Next one. Let's see what happens if we try to plug in 6. If we try to plug in, we would get 6 squared minus 36 equals 6 over 6. And that's all equal to 0, 0 over 0, which is an indeterminate form. I might go ahead and write that down. Indeterminate form. And that means that we really can't make heads or tails of it in this form. And what we need to do is rearrange things, try a new technique. So we will learn some more powerful techniques later on. One of them would be called L'Hopital's rule, and it uses the derivative that we will soon define and start using. Not quite ready for that yet. And so the tactic that I'd like to take towards this problem is just doing a little bit of algebraic simplification before we, actually plug in 6 and try to evaluate the limit. This is one of those cases where we have a removable discontinuity. I'm going to show my work down here so that it all fits on the screen, and maybe we don't have to, move around too much. Okay, so if we change x squared minus 36 on top into x plus 6 times x minus 6, and we have over x minus 6, that allows us to cancel x minus 6 factor on top and bottom. And then instead of evaluating the limit as x goes to 6 of the whole thing, we can evaluate the limit as x goes to 6 of just what's left. So we've used kind of a little algebraic trick. We've factored the top and canceled common factors, so that in the end, we get a limit of 12. And maybe real quick, it might be worth our time to look at GeoGebra and just verify that that's true. So if I've got x squared minus 36 divided by x minus 6, yes, this thing turns into something that looks a lot like a line, a lot like the line y equals x plus 6. And if we go to, let's go ahead and put a point on this line, and we'll make it be able to go up to 10, and let's just, oh, come on. 10. Not letting me type over here. Come on, there we go. Let's just move up by 1 so that yeah, there we go. Okay, so we can go from -10, or sorry, -5 to 10. And I'm gonna make the point A, f of A, so that we just get a nice point on that line. And you can see that for all of these values, plugging in -2 into this function would give us a completely normal fraction, and actually the fraction would be equivalent to 4, so no big deal there. We get to here and notice that that point just drops out, because that is a point of discontinuity for this rational function. You know that in the pattern, it does look like we'd be aiming towards y equals 12 as the value that we are approaching. So from the left, from the right, we are approaching 12, just like we found numerically here, analytically. All right, so this one was easy just to plug in. This one we could plug in after a little bit of algebraic playing. This one will be similar as well. This is maybe level 2 of algebraic simplification, but here we use something called the conjugate on top to multiply the fraction on top and bottom by the conjugate of this numerator. Because right now, x is going to 0. Again, we're in the situation where we have a 0 over 0 indeterminate form. So we need to pull some kind of algebraic trick off so that we can get this into a new form. All right, so the square root of x plus 5 plus the square root of 5 is the conjugate of this. And the idea is this is coming from the difference of squares factor pattern, so that the middle terms, when we multiply these things together using the distributive property, we'll get the square of the first term and the square of the last term, but the middle terms will cancel out. And that should be nice for us when we're evaluating the limit. So let's go ahead and rewrite the limit as x equals 0, or x goes to 0, or 0, not infinity. And now we multiply through by the conjugate on top. On top, we get x plus 5 for the square of the first term. We would have square root of 5 times the square root of x plus 5, and then we would subtract 5 times the square root of x plus 5, so those middle terms cancel out. And then the last term would be minus 5. So now the top of that fraction is just x. And on bottom, we have x times x plus 5 plus the square root of 5. So let's keep going. Now, so we could treat those as 0, the 5 plus 5 and minus 5. We could also, now that those are gone, cancel a factor of x on top and bottom, so that all we're left with is the limit as x goes to 0 of 1 over the square root of x plus 5 plus the square root of 5. And now if we try plugging in 0, we get 1 over the square root of 5 plus the square root of 5. So this is 1 over 2 times the square root of 5, which is a perfectly fine number. Yeah, that is algebra trick level 2. And the final one here, where we've got the limit as x goes to negative infinity of e to the x times the sine of x, that will be 0. But in order to prove that, there's no like algebra trick. Plugging that in gives us, e to the negative infinity. You're thinking about that does approach 0 over time. Sine to the sine of negative infinity kind of just keeps oscillating between 1 and -1. So you have this weird thing like, okay, we've got 0 times some number between 1 and -1, and there's not really a clear-cut answer with the tools that we have right now. What we are going to learn later is that this one's going to be really nicely handled using the squeeze theorem. And we will, see that soon. So this is the kind squeeze theorem where the general idea of that will be this function e to the x times sine of x. It's the product of those two things. So we will have some waviness, but we will start off close to 0 on the left and then get bigger and bigger as time goes on. So if you're thinking about the graph of that, shoot, that was poor start. Something like that. And actually, the squeeze theorem is going to come into play because what we'll be able to do is squeeze this crazy function in between one that is more well-behaved, that borders it on top, and another one that's well-behaved and borders it on bottom. And the idea is if the well-behaved one on top and the well-behaved one on bottom both approach 0, then the one that the crazy function that's always in between the two gets sandwiched in between them, and therefore the limit also needs to be 0 for the weird one. So yeah, we'll see that soon. All right, so these are our options. Either just plug in, do some algebra right now, and pretty soon we're going to learn about the squeeze theorem. That's basically what we're looking forward to in this chapter. Throughout this chapter, we're going to look at a bunch of limit laws, which should work the way that you expect them to. Here we are combining limits for different functions, but we're approaching the same point C. So in all of these, x is going to continually approach some x value C. But these are just different ways of combining limits and the functions and operations that we already kind of know how to work. And they work the way that like you would expect, kind of like they're almost distributive. Yeah. And again, we are talking about limits because we are about to define calculus in terms of limits. We saw at the very beginning of this section that doing the limiting process on a difference quotient gets us really, really close to the instantaneous velocity, getting a tangent line for a slope. It's these limits kind of underpin all of the other cool stuff that we're going to do in calculus. And so it's just an important foundation. Yeah, these limit laws, I wouldn't necessarily expect you to write these down, but just realize that they behave the way that you would want them to. If you multiply a function times some constant k, the limit of that transformed function is the same as k times the limit of the original function that you started off with. It's like you can pull k out of the limit. These things work the way that you would expect. So one of the reasons that we have these limit laws is that sometimes I don't know, combining these functions is not always easy to describe. For example, number 2 here. Um, we have f of x defined as a piecewise function, and g of x is just cosine. But if we want to find, for some reason, we want to find the limit of the product of f and g, down here, it would be nice to know that using a limit law, that the limit of a product is the product of the limits, and that this thing would equal the limit as x goes to 0 of f of x, and all that can be multiplied times the limit as x goes to 0 of g of x. And know that at any point during this whole thing, if one of these limits fails to exist, then the entire thing is going to fail to exist. So it allows us to decompose more complicated limits into smaller things. Cosine, that part is no big deal. From the left and from the right, cosine would approach 1 when x approaches 0. So this part of our product is just going to be 1, and that's nice. F of x, on the other hand, is a little bit more complicated. We've got the absolute value of x over x. And the way that I like to think about this one is some cases. So for this part, let's use some green. For this part, if x is negative, then we would have a positive number over a negative number. And, well, actually that number would be the same thing. You know, we would get -1 overall, because we'd have like +3 over -3, and that's -1. If x is positive, then we would have a positive over a positive, and we would have 1. So the limit from the left here does not match the limit from the right. And yeah, let me show you on GeoGebra just to make sure we're all on the same page here. Let's clear that. Don't save. Bye. Absolute value of x divided by x. Yeah. From the left-hand side, everything is -1. From the right-hand side, everything is 1. And so the left-hand limit does not match the right-hand limit, meaning that the overall limit for f of x does not exist. And therefore, does not exist times 1. Now, the whole thing does not exist now because one of the parts of the limit fails to exist. So that's one of the things that these limit laws can help us do, especially when we have functions that are hard to describe. It allows us to break things down so that we can evaluate things separately. All right, moving on. So we looked at these 5 limit laws so far, but there are extensions that can be, proven based on the ones that we have so far. Here is a little example of, we can use the product law to get the limit of a function times itself to be the limit squared eventually. And you can do the same thing for multiplying the function times itself 3 times, so cubing it. And that leads us to the integer power law. There are sometimes more detailed proofs of how these things come about in the back, but right now, let's just take a look at these laws, and then it's just nice to look at them because they behave kind of the way that you normally would expect things. So the limit of a power is a power of a limit, that kind of a thing. Sometimes I like to think of it that way. But yeah, powers play nicely with limits. I guess that's the story. The limit of x approaching any number c of the function like y equals 1 is just 1. That makes sense. And then if the function's y equals x, the limit as x approaches c is c. Those are kind of two foundational limits that we can use, substitute in, and prove a lot of other things. So there are a few more laws here. Polynomial substitution law. The limit as x approaches c for some polynomial, p of x, is always going to be p of c. And I have written down here to remind me to ask, what does that say about the continuity of polynomials? If the limit of p of x as x approaches c equals p of c, that pretty much already automatically says that polynomials are going to be continuous everywhere at all points, because c is not special here. That's really cool. Polynomials, always continuous. We're going to be able to do calculus on them. I guess one of the things that I haven't said yet, or said yet today, is we're going to be looking at continuity, because continuity is a prerequisite for us to be able to do calculus on things. Continuity needs to happen so that we can talk about instantaneous rate of change, and we can talk about accumulation. The functions that we work on need to behave nicely and be continuous. Okay, so another one, rational substitution law. Here we just have a polynomial on top of another polynomial. So it makes sense that just substituting in C is going to work for all rational functions. The only place that you might encounter a hiccup is when the denominator would equal 0, because that means that the whole expression is undefined. And so, yeah, rational functions as well are going to be continuous on their entire domain. And technically, C will be a point of discontinuity, but at the same time, according to the definition of continuity in this book, we will call any rational function a continuous function on its domain. And then another one, we've got the positive integer root law, where very, very similar to the integer power law, we've got roots now instead of powers. Those behave nicely with limits as well. And sometimes it's a lot easier, to evaluate the limit of f of x rather than evaluating the nth root of some function of x. You know, it can be handy sometimes. Rational power law is pretty much combining the integer power law with the positive integer root law. That, yeah, since both of those things are true, rational power law works out as well. So again, cool. Just to review, for determining limits when direct substitution doesn't work the first time you try it, the first one would be algebraic simplification. If we can just simplify it and solve, great. In this case, if we put in -3 on top and bottom of this fraction, we're going to get 0 on top and bottom. which means that we're in an indeterminate form. And so what we do is factor the top and get x minus 3, x plus 3 over x plus 3, cancel out the common factor of x plus 3, and we're just left with the limit as x approaches -3 of x minus 3. And then when we substitute in -3, we get -6 there. So that's great. And again, for example 6 here, this is just the trickier version. We're going to multiply by a conjugate here because we see that we have a square root on the top. And when we plug in x equals 1, we get 0 over 0 again. And so this is really just, yeah, a trick. And this is what it would look out. I already did this up at the top, so I don't think we need to go through step by step again. But I don't know, even if you wanted to, you know, pause and try it yourself, you could. But at this stage, just knowing that multiplying by the conjugate will make things work out nicely, it's really more of a trick than anything. That's great. That one works out to be 1/4. Okay. The squeeze theorem is the next big thing that I think we should spend some time on because that's new. Again, the squeeze theorem, we use it when we have a nasty function in the middle, but we can bound that nasty function on top and bottom by more well-behaved functions. And so f of x is our nasty function, g of x and h of x are better behaved ones. And if g of x and h of x both approach the same limiting value for a certain value or for a certain x value c, then the function that's always in between them gets squeezed to that limit as well. And a proof is in the back of the book, probably involves epsilons and deltas and that kind of great stuff. So if you want to go look at that, please, that's fine. Let's take a look at how we could use the squeeze theorem to prove that x times the sine of 1 over x is 0. So one of the things, if you were to encounter this thing in the wild, one of the things that you might try is the product limit law, which means, you know, hey, we've got x times the sine of 1 over x. What if we looked at each of those individually? And pretty quickly, we will see that this won't be too helpful. We would have the limit as x goes to 0 of x, and we'd multiply that times the limit as x goes to 0 of the sine of 1 over x. And on this first one, let me go ahead and zoom back in so that you can see my writing a little bit better. This would be 0. And this one would be does not exist. Remember, sine of 1 over x is that one where we have the oscillating discontinuity and the thing just keeps oscillating as it gets closer and closer to 0. This is one of those cases where it might seem nice to just call this one does not exist, because one of the parts of that limit doesn't exist. But in this case, since we have 0 times a limit that does not exist, there still is maybe some room for a limit to exist and be 0. In the case that we looked up here, where we were looking at a product there, we were multiplying it times 1, and there's no way for 1 to kind of fix things and squash something that doesn't exist down to 0. Right now, the only reason that the hope is staying alive for some kind of limit to exist is because the 0 is there. But right now, our limit law is kind of not giving us enough of a tool to be able to evaluate this limit, because x times the sine of 1 over x is a nasty looking function. And actually, this might be a good time to look at it on GeoGebra. Let's look at x times the sine of 1 over x. Yuck. All right, zooming in a little bit. Yeah. So here we have, I wasn't necessarily expecting this to be an even function, but it does make sense that it's an even function. It's symmetric about the y-axis because x is an odd function and sine of 1 over x is an odd function. So multiplying them together actually makes things even. But anyways, what we're going to try to do is come up with 2 functions that are more well-behaved, but still would come to a limit of 0. And maybe zooming in would give us a better indication of the kind of functions that we might be looking for. On the top, the absolute value of x is going to work really nice. And that largely comes about because the sine of 1 over x is going to continually oscillate between 1 and -1. And so it's never going to get bigger than 1. And so, yeah, this whole expression is never going to get bigger than the absolute value of x. And on the flip side, if we take the opposite of that, then we get this lower boundary where we're never going to get lower than negative absolute value of x. And even if we go and zoom out, we can see that that always holds because sine always oscillates between 1 and -1. And so these more well-behaved functions can act like a top function for us and a bottom function. And the way that it would work out writing things is that we would squeeze this limit, the limit as x approaches 0 of the nasty function that we're looking at. Well, actually, I'm going to flip-flop that so that we're, nicely reading it from left to right. The limit as x goes to 0 of the absolute value of x, and the limit as x goes to 0 of the, hold up, sorry. On the left-hand side, the less than, we want negative absolute value of x. And on the top side, we want just regular absolute value of x. And that works because sine of 1 over x oscillates between 0 and 1. The range of this function is -1 to 1. That allows us to create this inequality. And if we evaluate the limit over here and we evaluate the limit over here, as x goes to 0, this limit will approach 0. And on the right, this well-behaved limit, again, will approach 0 from the left and from the right. Both ways approach 0 on the absolute value function. And that squeezes the function in between saying that its limit should be 0 as well. So we get what we set out to prove, that this thing equals 0. So that's squeeze theorem. Yeah, and later on we'll use L'Hopital's rule. That'll be cool for finding key limits as well, but that involves derivatives, which we have yet to derive. All right, we're in section 2.5 now, on to continuity. The first definition is continuity at a point, and we've seen this already. It happens when the overall limit equals the function value at a certain x value c. Right continuity and left continuity are actually things. And so I think that came up in our activity. Real quick, do I have? Yes. A lot of us were wondering right at the beginning, because I threw this on there without really, not all of these different categories apply equally well to each one of these points. But we were asking ourselves, is the function here continuous at this point, at x equals 0? And while we don't have anything coming from the left, so we don't have any left-hand limit, we do have a right-hand limit. And if the domain is just defined for non-negative real numbers, then having a right-hand limit match the function value here means that we're right continuous, and that's completely fine. So, on this part on our activity, saying that we have right continuity is the correct thing to do. Going back here. So right-hand continuity, left-hand continuity, cool. Going back to continuity in terms of delta and epsilon, don't worry, I'm not going to focus on this too hard in this section, but I wanted to point out that the only difference here from the delta epsilon definition that we've seen before is the fact that we have f of c right here in place of L in the entire definition. That's really all that's different. And notice that f of c is hanging out where L generally is as well here. So we're continuous when the limit equals the function value, and the function value is just being substituted in here for L. That's the delta epsilon definition of continuity. Both of those are continuity at a point, and a lot of times it's nice to talk about continuity of an entire function, so all of the points in that function at one time. And when we say that a function is continuous, we are implying that we understand that we're talking about continuity on its domain. So if there's an x value that's not in the domain of the function, that discontinuous point does not count against being a continuous function overall. It's a little bit paradoxical, but we'll see that. So the function 1 over x is continuous on its domain because the only point of discontinuity would be where x equals 0. And since x equals 0 is not in the original domain of the function, we can still say that overall 1 over x is a nice continuous function because at every other point, this function's nice and continuous. But if we were going to be tricky, and if you were asked, is this function continuous on the interval -3 to 3, just looking from here to here, technically the answer would be no there, because we've specified a different domain where 0 is part of this interval. And so having a discontinuous point at 0 means that we would not be continuous on that entire interval because there would be a discontinuous point. So I know that this is a little weird, but continuous functions can have discontinuous points as long as those discontinuous points are not in their domain. I guess that's the best way to say it. Cool. And again, for example, number 4, we'd be in a situation where if we were looking at the limit here, we'd use a little bit of algebra. We would cancel out the x minus 1 on bottom and the x minus 1 on top. And for finding the limit, that would be fine. We would just get 2 for the limit there. But know that as x approaches 1 here, we would be in a situation where the function is undefined. But since that undefined point, that discontinuous point, happens at a place that's not in the domain of the original function, it's fine to call this continuous overall. So it is a continuous function and simultaneously has a discontinuous point at x equals 1. It's weird. Cool. All right, so similar to limit laws and stuff, we've got some properties of continuity. A sum of continuous functions is continuous. A multiple of continuous functions is continuous. All of these good things that we would like to be true are indeed true. So when we're combining continuous functions together, they stay continuous, which is great. I guess there's an exception where you don't want the denominator of a fraction to be 0, but we're pretty used to that. Cool. Those are, yeah, nice. This next one is about a limit passing through a continuous function. All that means is that when we're working with a continuous function g, and g is continuous at a, you're going to be, when you take the limit as x approaches c of g of x, you're going to get a out of that, and you're going to get f of a is the thing that you're, looking for. So all that's saying is that when g is when g is continuous at c, all of these are true, and it's almost like you can pull the function f outside the limit and just evaluate the limit of g of x rather than the whole composition. So that's nice when you know that the inside function is continuous. And again, these kind of things can be proven with deltas and epsilons, and it gets really gross, and that's why they throw it in the back of the book. All right, the final couple things that we're going to look at. A composition of continuous functions is continuous. So kind of piggybacking off of this, that's cool. And the inverse of a continuous function is continuous as well, as long as, the domain considerations are met. Cool. So yeah, f has to be one to one and continuous on a given interval so that it actually has an inverse. This was the last example that I think I was planning on looking at today. There's one more thing after this that could be mentioned about trig functions and exponential functions also being continuous. And there's a little alternate formulation of continuity that can be used there where you think the limit as h goes to 0 between two, things where h is just a little distance between 2 points that are next to each other. Know that trig functions are going to be continuous. Know that exponential functions are going to be continuous. But going back here, maybe we can use the different properties of continuity to kind of decompose these things that are nasty and think about when these functions will be continuous. Pretty much everywhere here, I see function composition happening. For part A, and our function f of x, we have a cube root function on the outside and then a rational function on the inside. And we know that a rational function is going to be continuous everywhere. It might have discontinuous points when the denominator is equal to 0, but notice that x squared plus 5 is always going to be positive. X squared is always going to be a positive number. 5 is always a positive number. So this denominator is never going to be 0. And so this rational function is continuous for all real numbers. And then a cube root function is also going to be continuous for all real numbers. We could show that really quickly using the integer root law for limits that we looked at earlier. But yeah, again, we're in the situation where the inside function continuous, the outside function, the cube root, is also continuous. So we have a composition of continuous functions, and that is continuous everywhere on the real number line. Part B gets a little crazy, primarily because we've switched from cube root to square root, and so we need to think about domain there. You don't want to put negative numbers inside of a square root, right? So on this one, not only would we be concerned with places where the denominator would equal 0, we would be concerned with places where the entire rational function is negative, because we wouldn't want to put a negative number into the square root. So those would be two considerations that we want to look out for. The bottom part can be 0. We can factor that a little bit. No, we don't want 9. Let's pull a 3 out. And let's pull 3x out, sorry. And then we've got 3x squared plus 1. So examining the denominator here a little bit, this would mean that x equals 0 would be a place where the entire denominator would equal 0. So that wouldn't be in the domain of the rational function on the inside. And otherwise, this part would always be positive, so we wouldn't have to worry about that. So x equals 0 would be one of those points that we want to avoid. And it's just not in the domain of, the original rational function. And then we would be concerned with doing the harder thing of figuring out when is this rational function actually positive rather than negative, because we want to avoid when the whole rational function is negative. And honestly, there's not like a straightforward way of doing that, especially because we have a polynomial up here where the degree is 5. There's no quintic formula to decompose that and find the roots. One of the things that I did earlier was I looked up Wolfram Alpha. Wolfram Alpha, super cool if you want to do hard math. I just typed in that polynomial and notice, hey, we can actually factor x plus 1 out of that and be left with a yeah, a quadrupolynomial over there. And so we do have one real root to this, the numerator, and that's -1, and there's 4 complex roots. But what that means for us back on this problem, whoops, is that for the interval between x equals 0 and x equals 1, the numerator of this would be negative and the denominator of it would be positive. So in between 0 and 1, we'd be putting in a negative number, and the inside function, or yeah, the inside function would be a negative number, and we wouldn't want to put that into the square root function. And so we end up looking at a domain that is everything except the interval from 0 to 1. And actually, I'm just going to look at the book here and show you what it says. But here's the graph of that rational function on the inside. This is a graph of the entire thing when you put a square root over the top of it. So yeah, here's the part in the book where we're saying, oh yeah, we only want the outer function is only defined when you're putting a positive number into the square root. And so we want to make sure that we're only dealing with areas where this is positive. And here from -1 to 0, okay, maybe I messed that up. Duh, sorry. -1 was the real root. I don't know why I kept saying 1. -1. We want to stay away from this area where the function value is negative. So basically what we do is just chunk out that interval, and we're left with the rest of the real line. And if we use numbers from this interval, we're great. Then we are in the situation where we are composing two continuous functions, and things work out great. And I don't know, similarly for the other two, we don't have to beat these ones into the ground. But know that the properties that we looked up here, these different theorems, are nice ways to be able to pick apart more complicated functions and discuss their continuity. Again, are we going to be doing this much for the rest of the semester? Not really, but it's good to have the foundations of limits down so that when we go on and we use those limits to define derivatives and integrals, that we are standing on a more firm foundation. So with that being said, we've done quite a bit of due diligence to limits and continuity now, and tomorrow, or I guess it'll be Monday, or gosh, I don't even know. All these are mixed up. The next class period when I see you, we'll be talking about section 2.6 and stuff, and we're actually going to define the derivative using limits. It's going to be a great time, and I look forward to seeing you then. All right, have a good day. Bye. Come on.